Okay, so this is where we were at the end of the last video. We're developing equations for electric fields. And I was showing you how they parallel the equations for gravitational fields that we used in the last unit. Okay, so this unit we're going to use electric fields. An electric field is an area around a charged particle where any other charged particle will experience a force. And we'll have two ways of finding that electric field. Two equations, either E is equal to FQ over Q, or E is equal to KQ over R squared. If you're using the E equals FQ over Q, then this Q is the charge brought into the field. Just like in gravitational fields, the M on the bottom was the mass brought into the field. And in the second equation, E equals KQ over R squared, the Q on the top, and this one, is the charge creating the field. And we often call this charge that's creating the field, we call it the source of the field, just like the Earth is the source of our gravitational field. Okay? Now people will say to me, well, how do I know which one to use? Well, that's dependent on what you're given. If you're given a force that a charge experiences when it's at some point in a field, then use the one with force. If the question's asking you how far, what's the strength of the field a certain distance from a charge, well, it's that certain distance from a charge, well, that charge is the source, and you're being given an R, so use the equation with the R. Now, the difference between gravitational fields and electric fields is that we always know which way gravitational fields are going. They're always acting towards the source. You never have to worry about which way is the Earth going to pull me today. It's always going to pull you towards its center, no matter what day of the week it is, no matter what your mass is, no matter where you are in its field, it's going to pull you towards the center of itself. But that's not true with charges, and it's not true with charges because that force, that electrostatic force, is a force of attraction or repulsion, whereas the gravitational force was always only a force of attraction. And so to get our directions of electric fields, we've had to define the direction. And I was telling you about this yesterday. We define it. It means we've gotten together as a group of scientists. And for the record, this was way before my time. But we've gotten together as a group of scientists and we've said we're going to define the direction of an electric field as the direction of the force that a positive test charge would experience if placed at that point in the field. So we take this tiny little positive charge and we place it anywhere around another charged particle, and the direction of the force that that little tiny positive charge feels, that will be the direction of the field at that point. And then we draw our lines to show it, and these lines are called field lines. So we can draw the field, then I'm just going to around a positive charge, okay, because if there's a little positive test charge out here, this positive charge, whoops, imagine that's straight, we'll push it away. And no matter where I put that positive charge around this central positive, around this source, the source will still exert a force outward. And so my field lines around a positive charge are always outward. But what if my source creating the field was a negative? Well, I bring my little positive test charge in. Remember, this is like your little positive brother, sister, cousin, next door neighbor, always positive and tiny. When you bring it in, this time if the source is negative, they're going to get drawn in. They're going to experience a force inward. And no matter where I put this positive charge around my negative source, it is still going to experience a force inward. Okay? And so around a negative charge, the electric field lines will always be inward. Now something kind of cool happens when we bring two positive charges, two sources together. Their fields are going to overlap. But remember when we were talking about field lines in the last video, we said that they can't cross. So imagine I have two positive charges, so two positive sources fairly close together, and I bring my little test charge here and I try to put it between them. Well, neither of them want it. So what's going to happen to the field lines is they're going to curve as they try to push it away. Okay, and so when two positive sources are near each other, their field lines will curve because they can't cross as they try to push that positive test charge away. If it was two negative ones, and I did the same thing, I put my little positive in here, they would both want it. And so again, our field lines are going to curve. They're going to look actually exactly the same as the ones above. The only thing that's going to be different is that the arrowheads will be in the opposite direction. Because this time they both want it. So they'll be trying to draw in that little positive charge. Sorry, I just couldn't put the arrowheads on while I was drawing it because I knew I'd screw some of them up. There we go. I think I got them all in. Okay? So I always think they look like spiders or octopus or something that are like happy to see each other. So like they open their arms out to give each other a hug or something. Now, what if they were oppositely charged? What if one was positive and one was negative? What would the little field lines around them look like? Well, if I put a positive charge in between them, a test charge in between them, the positive source wouldn't want it, the negative would, and so they'll actually work together. And so our field lines will go from the positive to the negative. They'll hook up. The positive doesn't want it, the negative does, so it's like, oh, well, let's help each other. Okay, and so they'll curve out like this. Away from the positive into the negative. Okay, now an interesting thing to note. So we always talk about a positive source or a positive test charge. So what happens if, and that's how we define these field lines. So they're not changing now. The direction of the field lines are set around a positive charge or around a negative charge. So what happens then if I bring a negative, okay, first let me bring a positive charge into the field. So if I bring a positive charge into the field, the blue lines are going out, and the force would also go out, right? And the same, so the force in the field for a positive charge will always be in the same direction. And that's true whether we're around a positive source or a negative source, right? Here's my negative source. I bring a positive charge in. It experiences a force inward. So the force is going in, and the field is also going in. But what if I now bring a negative charge? Okay, I'll put it over on this side okay, so this time I'm going to bring in the field. There's a positive charge here, and I bring a negative charge into the field. Well, the field is still going out because it's defined by our test charge. So the field is going out, but the force is going in. So when you are bringing a charged particle into the field, if that charged particle is positive, the field and the force will be in the same direction. If that charged particle is negative, the field and the force will be in the opposite direction. Okay? Because the negative will want to, in this case, move inward, even though the field would be pushing out. Okay? If I bring it over here, negative, the field's going in, but what force will my negative charge that I'm trying to bring into this field experience? It'll feel the force going out. So again, the field and the force for a negative charge will always, 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 always be opposite. Whereas the direction of the field and the force for a positive charge will always, 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 always be the same. Okay, so tonight when you're doing some of these questions, especially with this equation,